Hi, in this video, we're going to talk about something called implicit differentiation. Implicit differentiation is a method that we can use to solve when we have uh, more than one variable. And it kind of applies itself um, to doing the problem. Let's suppose we had a problem like this. Um, y equals 2x. Pretty easy, huh? Well, when we're taking the differentiation of this particular problem, we kind of said, well, using the power rule, it's 2, huh? But let's analyze this a little bit more. We're going to use this notation, dy over dx equals. When we take the differentiation of 2x, we actually get 2 times the derivative of x. And this would be the derivative of x with respect to the derivative of x. And dx over dx is just simply 1. So that's why we end up with 2. We're actually using the chain rule on this. We're taking 1 times 2, 2, and then the derivative of x, dx over dx. But for a shortcut, we just called it 2. But in these kind of problems, we have to be more specific. Let's take an equation of a circle. X squared plus y squared equals 25. This is the general equation of a circle. Here's your x-axis, here's your y-axis, and this would be, the square root of 25 is 5, so the radius of this circle is approximately 5 units. Well, it's exactly 5 units. So this would be a picture of the circle. This would be 5 here, 5 units. So that's what we call, the equation of a circle. But let's find what the derivative of this is. Well, to do that would be kind of difficult because we have to solve this for y. So y squared, we have to bring over the x squared to the other side, makes it 25 minus x squared, and we got to take the square root of that. And then we have to do a bunch of other stuff to it. And maybe on top of that, we want to find out, we want to write an equation of the tangent to this circle at the point, let's say 4. And we just want to find what's the equation of the tangent at that point at 1, 4, which would be maybe up there someplace. And we want to know what's the equation of this tangent line. So to do that, we're going to use a technique called differentiation, the implicit differentiation. So we're going to take the derivative of x squared, which is 2x, but we're going to get a little bit more formal and say now we're going to use the chain rule and we're going to take the derivative of x with the derivative of x. Plus we're going to take the derivative of 2y, of y squared I should say, which is 2y, derivative of y with derivative of x. So we're taking it in respect to x, the derivative of x with respect to x. And of course, what's the derivative of 25? This would be just 0. Okay. So now what I'm going to do is I look at this and I say, well, dx over dx is just 1. So this is simply 2x plus 2y dy dx. So a lot of times when we're doing this problem, people don't rewrite the dx over dx. I like to just to show that I did the derivative things because sometimes the problems are more confusing. So now I'm going to take this 2x to the other side. I'm going to solve this for dy over dx. I'm going to solve this for the first derivative. So I'm bringing the 2x to the other side. And that gives me 2x, negative 2x plus 0 is negative 2x, right? I had a negative 2x both sides. And now I'm going to divide both sides by 2y to get this should be a dy, to get the dy over dx. I'm just going to jot it there. Dy over dx. These cancel. The negative 2 and the 2 would leave me with negative x over y. So now I've solved this for dy over dx. And what is this? This is actually the slope of the equation. So if I want to find the slope at that given point, I'm going to substitute in for x, I'm going to put negative 1, negative times 1, and for y, I'm going to put 4. The slope at this point would be negative 1/4. Okay, now I want to find out the equation. Y minus y sub 1 equals m times x minus x of 1. So I'm going to have y minus y sub 1, which is 4, equals m, which is negative 1/4, times x minus x of 1, 1, x1, y1. So I'm just going to solve this. Y minus 4 equals negative 1/4 x plus 1/4. And I bring over the 4. So my equation of y would be negative 1/4 x. This would be this tangent line plus 4 and a fourth. And there's my equation. We can see the lines going down. At 4 and 1/4, if we go through 0, it's going down 1 and over 4 and hitting the line somewhere, at 1. So this would be my equation of it. Okay, most of the time we're not going to be doing something that complicated. Most of the time we just want to get this in a form where we can find the first derivative right here. That's what we're really looking for. So let's try one in the book before I totally confuse you. And let's try one here. This is a little bit interesting problem. Okay, so they want us to find the first derivative of this, and then it says find the slope of the tangent line to the curve at the point 0, 3. Well, let's not worry about that right now. Let's just get the first derivative. Now, right here, I said this is going to be fairly easy. This is going to be easy, but right in here, I see we have an ABBA. There's a multiplication there involved. So let's see what we got. First derivative is 3y, but not just 3y squared. It's going to be dy over dx. We're kind of, you can almost think of it as saying, well, we took the derivative of the y. Okay. Then this is going to be plus x squared, we're not doing any derivative, times the derivative of y to the 5th, which would be 5y to the 4th. And again, we're taking the derivative of y. Plus b, which is y to the 5th, times the derivative of the x squared, which is 2x. And then I'm going to write down dx over dx, kind of showing I took the derivative of the x term. It's really the chain rule, but sometimes it's easier to think that way. Minus, now I'm going to do the x to the 4th, so that would be 4x to the 3rd. And again, I'm taking the derivative of x. So I'm writing down the variable that I'm taking the derivative. Like this was an x term, this was an x term, took the derivative of the y, took the derivative of the y. And then finally equals 0. Okay, and the next thing I'm going to do, because this has a lot of terms, I'm going to put the y terms together and the x terms together. And I'm going to probably put these in the parentheses. So I'm going to factor out, I'm going to look at this part of it and kind of factor out that dy over dx, because it's common to both those terms. So I could put it in the front or the back. It doesn't really matter. I'm going to write it like this. 3y squared plus, I'm going to put this in order, 5x squared y to the fourth. That whole thing times dy over dx. Plus, I'm going to do the same thing here, kind of simplify that. This would be 2xy to the fifth minus 4x cubed dx over dx. And of course, dx over dx is just 1, and that equals 0. So I'm going to take the part that was dx over dx to the other side. So I'm going to have 3y squared plus 5x squared y to the fourth dy over dx equals, and I'm going to just bring this over to the other side. And this is, you're going to change signs. Negative 2xy to the fifth plus 4x cubed. Now I want to solve this for dy dx, which is my first derivative or the slope. So it's very simple. I'm just going to divide this off both sides. You could write this down, or sometimes you just do it in your head. 3y squared plus 5x squared y to the fourth. So these will cancel, and there's my derivative right there. Here's my first derivative. See, it doesn't have to be super hard. I think I've got it maybe a little bit different form from the book, but I've got this. So the next thing it said, let's find the slope of the tangent line at 0, 3. So this is our slope. And it says at 0, 3. So wherever there's a x, I'm going to put a 0. And wherever there's a y, I'm going to put a 3. So this is negative 2 times 0, let's see, times 3 to the fifth plus 4 times 0 to the third. That looks like it's just plain old 0, doesn't it? Okay, on the bottom I have 3 times 3 to the second plus 5 times 0 to the second, 3 to the fourth. Well, this is going to be 0. This is going to be 9 times 3 is 27. So I got 0 over 27. 27 goes into 0, 0 times. So the slope at that particular point is 0. And they kind of show in the book that this curve right here at 0 goes up to about, I think this goes up to 3. And the curve kind of comes in like this and then comes back down and goes like that. So right at this point, the slope is 0 because the tangent line is horizontal. So it's really not too hard. We're just taking the derivative of each part. Just have to be careful once in a while. They throw in an ABBA or something like that. But when you take the derivative, now you're not taking a derivative here. You're not taking a derivative here. So you don't have to write dy over dx. Only the variable you're taking the derivative, or when you're taking the derivative and what the variable is. Let's try another one. See if we can do it. Here's one that isn't too bad. Y cubed plus 2x squared y cubed minus x to the fourth. Isn't that the one we just did? Almost the same thing. Let's try a different one. That one's just about the same thing we did. Let's try this one instead. Xy squared plus 2x cubed y cubed equals y plus 1. Now, that's an interesting problem. I think it's easier to get it equal to the number right away, so I'm going to bring over the y right away. Don't necessarily have to do this, but it'd probably make it easier when we go to simplify. So that's going to be minus y equals 1. Okay, So unfortunately, I got an ABBA here and an ABBA here. So A times the derivative of B. Okay, say it to yourself. Derivative of B, 2y dy dx plus, see, I've got to do the whole ABBA, y squared times the derivative of x, which is 1 dx dx. I'm just it's just the way I was taught to always write the dx dx. Plus, I'm going to put the 2 with the x cubed. So this is 2x cubed times the derivative of b, which is 3y squared dy dx times b, which is y cubed. See, I'm not taking the derivative, times the derivative of the first term, which is 6x squared dx dx. Run out of room. Minus the derivative of y, which is minus 1 dy dx equals 0. Geez, just was able to squeeze it in there. Okay, so we got some dx terms and we got some dy dx terms. So let's put these together. We can simplify as we put them together. Let's put the dyx together. So this is 2xy dy dx. Here's another one. This would be plus 6x cubed y squared dy dx. And finally, I got the minus 1 dy dx. Let's put the dx, so I got rid of this term, and this term. Now let's put the dx's together. We don't necessarily have to write the dx over dx. Be y squared times 1 plus 6x squared y cubed equals 0. And does it have a dy dx goes to the other side? So I'm going to save a little bit of time and just write this. I guess they're both negative. It won't matter. Okay. Factor out the dy dx on this side. 2xy plus 6x cubed y squared minus 1. And we're going to divide both sides by that. So that's going to cancel out here, and it's going to give me 2xy. Order isn't important. 6x cubed y squared minus 1, just so you have those two things. And that should be our answer to this problem. So hopefully that helps you a little bit. Sometimes they can come out a little long, and maybe there's something else. Here we could have factored out a y squared, but it wouldn't have really canceled anything on the bottom. So I'm just going to leave that. All right. Here's another equation on page 290. They got this problem. X equals the square root of 200 minus p cubed. And we want to solve this in terms of dx. So this would be 1 dx dx equals, well, this is under here. This would be 200 minus p to the third to the 1/2 power. So here we got a little chain rule action going. I got 1/2 200 minus p to the third to the negative 1/2 times the derivative of the inside. Derivative of 200 is 0. And then, now, when I did this 200 minus p to the third, I'm not putting down dp over dx because I haven't really, I just used chain rule and I haven't really taken the derivative of the p yet. So now I'm going to do the minus 3p squared dp dx. So now I'm doing it. It doesn't always have to be dx. And this one it was. Sometimes we do it in terms of time or whatever. So how can I rewrite this thing? What a mess, huh? I'm looking at the book trying to give me a hint, and I guess this is the best way they do it. So dy over dx would say this would be just 1 equals, let's pull this down to the bottom. This would be 200 minus p cubed to the 1/2 power. And then this would be negative, I guess I don't need a 1, negative 3p squared on top, dp dx. Okay, so they want to solve this for dp over dx. So what we're going to do is use the reciprocal of this. We're going to multiply both sides by 2 times, which is going to flip this over. In other words, dp over dx equals this times 1. So it'd be 2 over 200 minus p cubed. And we could put it under a square root if we wanted to, over negative 3p squared. And we might bring the negative to the top, like that. Or keep it on the bottom. Okay, so what I did is I multiplied both sides by the reciprocal. I don't want to write all that down, but I put the reciprocal here and the reciprocal here. Just put our reciprocal. Saved a little bit of work. What if we had one like this? And we want to solve this in terms of time, change in time. So the derivative of this would be dA over dt. See, it wouldn't be just 1, because we're not solving, we're going to solve in terms of time. The derivative of this would be 2 pi r dr over dt. See? Now, let's see if we can actually solve a problem using this. So what we did is we started out with a formula and we rewrote this formula in terms of using dr over dt and things. So in this problem, it says the restaurant supplier, this is on page 290, services the restaurants in a circular area. And it says, in such a way that the radius keeps increasing at 2 miles per year. Every year, say they start out as 1 year, the radius increased to 2 years. It started out as 1 year, now it's 2 years. It's increasing at 2 miles per year. At what moment, when R reaches 5 miles, gets way up here to 5, what is the area going to be? See how the area is changing? But the area is changing at a different rate. It's changing, it's getting bigger, but not twice as big. It may be changing at a very different rate. It's actually changing at 2 pi rate. So it's changing about 6 times as much. So what we want to find out is what's going to happen to this thing. So what we're trying to do is we're trying to find the change in the area. That's what we're looking for. How fast is this area changing? Or it's actually asking for the speed at which this area is increasing. It's increasing at a slightly different speed. 2 times pi. Now for the radius, we want to use 5 because that's what our final answer is going to be. And dr dt is the rate at which the radius is changing. The rate at which the radius was changing was 2 miles per day, per year. So that would be the rate at which it's changing. It would be 2 per year. Okay, so this is telling us how fast the area is going to be changing. So it's 2 times 5 is 10. 10 times 2 is 20. 25 miles per year. And it'd probably be square miles, I wonder. And that's how fast the area is changing. So it's 25 miles per year. So that's what we mean by kind of related rates. We'll work on some more related rates later. Let me try one more problem real fast. See if we can solve this problem. And we want to find out what's going to be the slope at this point to -1. We want to find out what's the slope of this equation. Let me get this book out of here. At that point. Okay, so this is an ABBA, right? So it's going to be A, no change, times the derivative of B, which is 4y to the third power dy over dx, plus B times the derivative of A, 6x squared, times dx over dx equals 0. This could have a 12y, and then we have a lot more working to do, but it usually ends up equal to 0. So what we're going to do is kind of combine this together. Let's see, this would be 8x cubed y cubed dy dx plus 6x squared y to the fourth times 1 equals 0. Bring that over. 8x cubed y cubed dy dx equals a negative 6x squared y to the fourth. And let's divide both sides by this. Just going to put divide. Okay. Write it down. It doesn't take that long, huh? Okay, so those cancel. Now, what we want to do is reduce this a little bit. Okay, 2 in the 6, 3, so that'll be a negative 3/4. 2 from 3 is 1, and x on the bottom. 4 from 3, y on the top. It's easier to reduce it. Now we want to find out what happens. What's the slope at that point? So I like to write the slope is equal to dy over dx is equal to negative 3 times negative 1 y xy over 4 times 2. I come up with 3 over 8. So the slope at that particular point is 3 over 8. Let's see if we agree with the book. This was actually from the book. This was problem number, I'm trying to find it. I don't even find it here. Maybe I just made up my own problem. Who knows? I don't even see a problem like that. I think I just made up my own problem. I don't even see one like that. But I'm going to take the assumption that that's correct. I don't know which one I was doing here. I don't know. Oh, here we go. It was number 7. I'm sorry. So I made a mistake on this. Unless I copied it wrong, and I probably did. Let's see. I wrote 2x squared. I combined two problems. I made it my own problem. Now, what if I wanted to find my tangent line? If I want to get real fancy, it would be y minus y sub 1, which would be a positive minus negative 1, equals m 3/8 times x minus x of 1, 2. And I could just simplify that down and get my 3/8 x minus 6/8. Bring over to 1 minus 1, which would be 8/8. And I could get my equation right here. I did it kind of quick. Hopefully I didn't make a mistake, but and I might reduce that, But that's pretty much the equation then of the point that's the tangent to this curve. So you do all kinds of things, fun things. I do more implicit differentiation in the next video using related rates. So let's stop this. Let's stop this while we're ahead.